once the gradient is done, what else do I need? Since we have previously studied Newton method, what would I also need? Look at the Hessian, why not, right? It looks, doesn't look very difficult. So, let's write this. Okay. Now, Hessian, again, I'm keeping J for the index of summation. So, I'm going to use I and K so that I don't get confused. This is the definition of the Hessian. Okay. So, my starting point again is this red expression over here. I have to take two derivatives, right? Or I can take this guy and then do what? Take one derivative with respect to xk, and then I'll be done. Okay, so let's do that. That will be simpler. So this is going to be equal to, so two terms over here. Let me underline it once again. This is what I'm looking at. I need to take the derivative with respect to xk. Okay, so this summation, the summation over j will remain. Okay, so drj x by dxk drjx by dxi. First term is as it is, and then the second term becomes rjx d2 rjx by dxk dx. Yeah. The first term again looks like something that can be simplified. What does it remind us of? I mean, if you got the gradient, this should be just as easy. The first term on the Hessian, what should it? Does it look like the product of two matrices? Yeah, what? The Jacobian matrix. That is clear that they are the product of two Jacobian matrices. The only thing that we have to get right is with the order, whether it's transpose or not, right? So nothing very great over here. I'm going to give you the final answer. This is simply J transpose X times J of X. So, oops. This is the first term. The second term is just going to be, I'm just going to write it like this. Okay, so Rj of X, and the second term, what would you call it? This is the Hessian of Rj, right? So we've got our gradient, we've got our Hessian. Hessian surprisingly didn't end up looking very, very complicated. You have two terms over here. So here is where the literature of least square problems kind of splits into two different approaches. Okay, and why it splits into two different approaches is simply because one is easier to do than the other. Why again? Because of the presence of a second order term over here. Okay, so if I were to ask you, if you look at the second expression over here, the Hessian has two terms. One is product of Jacobians. The second is a Hessian over here multiplied by this. If I wanted to ignore the blue term, okay, so there are two terms. This is engineering. So we are trying to see under what situations can the second term be ignored. That's what I'm asking. So when can we ignore this blue term? Basically, there seem to be two options. First option is what? What would you say? So product of two terms. Either the first term is low or the second term is low. There is no other possibility, right? So supposing Rj is small, that is one possibility. If Rj is small, Again, in plain English, what would that mean? I'm somewhat near the solution. If I'm near the solution, the residual is going to be low. So if I think of this as an iterative process and I'm arriving close to my solution, Rj is going to be small. Does that mean that doesn't necessarily say anything about the Jacobian? Jacobian is going to be whatever, right? So Rj is small. This, for example, when close to a solution. Okay, very good. Any other possibility? The second term, right? So when does this happen? When will del squared r be small? I mean, you already know the answer. If you were to take a common sense guess, when is this second term going to be small in magnitude, what would you say? Supposing your model was linear. If your model was linear, then there is no second order term that's identically zero. That's the trivial case. But if it were sort of weakly linear, right? So, for example, if R is approximately affine or linear, then the second derivative of it is going to basically be either 0 or very close to 0, right? So these are the two possibilities when we can ignore these terms, okay? And when I ignore them, what do I get? I get that the Hessian simply becomes J transpose J. Because the second term is gone, and this is what is called in the literature as linear least squares. Okay. We will also talk about nonlinear least squares when the second term cannot be ignored. Okay. As you can imagine, there is computationally more work is involved in solving a nonlinear least squares problem. So before we go to nonlinear least squares, we will spend now some time looking at linear least squares problems because they appear so often, and we have already spent some part of the course looking at linear least squares problems. For example, when you solved Ax equal to b, Ax equal to b, I wrote it as norm of Ax minus b, for example. That is a linear, the model is linear, and I'm trying to minimize it. So it's a least square minimization problem. So I've already looked at it, but what I'll do is I'm going to put it into the language of that we have just discussed so far. Okay, and we'll look at, for example, this minimum norm solution which I mentioned, or how to use the SVD. When can we truncate the SVD? All of these tricks which are there found all over numerical analysis, we'll have a look at it now, okay, in the context of linear least squares problems. So let's look at this now. So this is a affine function, which implies that R of x is simply something like this, Ax minus b. This is as general a linear expression as I can find. So my objective function I had said was half of norm Rx squared, right? So that will continue over here. So this is just going to be a good kind of a revision for all of you because you are very familiar with all of this now, right? If I take grad f, I don't need to remember anything of what I did just now. If you look at this expression and calculate grad f, what will you write? Using what we did in the very beginning of the course, right? Taking the gradient of something like this, what should you get? Multivariate chain rule. A transpose multiplied by you shouldn't forget this. X minus b, exactly right. This is how we had from first principles, if you remember, when we had tried to take the derivative, we had done it for the gradient, we had done it for the Hessian. This is grad f, right? This expression will come so many times. It's useful for you to just sort of keep it in your memory, because whether you're going to do ML or whatever, this expression will come again and again and again. It's useful to remember this. Okay. Now Ax minus b is also my residual. So I can write this as A transpose Rx. Okay. And if I look at the language of least squares over here, where did it go? Okay, here you go. In a linear least squares problem, this was J transpose R. Not surprisingly, here I have A transpose R. So it implies simply that the Jacobian is the same as A. I'm trying to take my well-known linear, Ax minus b problem and fit it into the least squares language. Okay, and that's fine. And then the second term is del squared f. Del squared f, what will it be? There is r is only linear, so second derivative of r is going to give me 0, right? So this is J transpose J, or in other words, A transpose A. This is what I get. Okay. Now, what supposing I wanted to do, for example, the Newton method or something like that over here, right? So for that, what is the requirement on the Hessian? Positive definite, right? So Hessian must be positive definite. Hessian must be. Is this expression positive definite? I hear several yeses. Anyone disagreeing? If A is invertible, okay, I tell you that, okay, so for invertible, that means what should the size of A be? A has to be square if I say invertible. But I said from the common sense point of view, I want more measurements than parameters. That means A is tall, fat or square? Tall. So A is definitely not going to be invertible. So A is not invertible, let's take. Is this Hessian positive definite? I hope someone will disagree. There is, that's important, it's not a given, right? So only when A is full column rank will this expression be positive definite. Why? So let us see, for positive definite, what is the definition? Anytime you have positive definite, what do you need to do? Stick a Z transpose Z on both sides, right? So if it is positive definite, oops, Z transpose, this should be strictly greater than 0. And what is the important qualifier? For all Z. For all Z, let's make it even more precise. There's one more thing, not equal to 0. This is the precise statement. Okay. Now this becomes Z transpose A Z should be greater than 0, and this becomes norm of AZ squared greater than 0. Yeah. Now if A does not have, if for example, if the columns of A are linearly dependent, then there will exist a non-trivial Z for which A into Z is going to give me the 0 vector. So it will be positive semi-definite. So this expression is always positive semi-definite, it's not positive definite. On the other hand, if the columns of A are linearly independent, right? So remember, what I'm talking when I say this is I'm looking at this. These are the columns, and I have a Z1 up to Zn over here. So A into Z is also linear combination of the columns of A. That is one picture of A into Z. If the columns of A are linearly independent, that means there is no linear combination of this which is going to give me 0. because they are linearly independent, right? So that is why A should have, you can say the columns are linearly independent, or a shorter way of saying it is full column rank, right? So A must have correct. So that's a good point. How, so this, so yeah, so Ruben has asked a good question. It depends on how you chose the data points. If you had a bad strategy, you could have essentially duplicated duplicate points could happen, for example, or you may still have it full column rank, but the condition number may be bad. We'll come to that analysis later, right? So choice of data points is important. I mean, and this issue is there all throughout numerical analysis. For example, have you heard of this Runge phenomena? You take an evenly spaced number of points and you try to fit a polynomial as a simple enough experiment, right? Take some function f of x defined from say 0 to 1 and take uniformly spaced points and try to fit a polynomial. Start with linear, quadratic, cubic and so on. As you start increasing the number of points, what happens? If you, it's a well-known thing, there's a nice Wikipedia page also about it. As you increase the number of points, the function approximation that you get, it goes through the data points very nicely, but in between those data points, you have a huge fluctuation that happens, right? And that's because you chose those points uniformly. On the other hand, if you choose the points non-uniformly, this oscillating behavior goes away completely. Okay, so and those non-uniform points often there is if you study numerical analysis, what are they called? Anyone has an idea? Wants to take a guess? Chebyshev points, for example, they're called Chebyshev points, different from uniformly spaced points. So there's a lot of deep analysis that goes into how to choose your measurement points. It seems naively just take uniformly spaced points. It's often not such a good strategy. So all of that will come into the numerical properties of A. Okay, and we'll come to that a little bit further down the line. But A must have full column rank for to be positive. Assuming this is the case, is f a convex function? Hessian is positive definite. Is f is a, clearly you can see it's a convex function, right? So f is a convex function. Okay. Therefore, if we find some point x star such that grad f of x star is 0, are we done? Then we are done. Okay. So what is the equation that I need to solve now to get this to finish this problem? Grad f equal to 0. Grad f, we already had an expression. Where was it? Grad f was here. A transpose Ax minus B, right? So grad f is equal to A transpose Ax minus B. Okay, and this basically becomes, right? We have seen this kind of equation before, and we have made one comment about this guy saying that this has bad condition number because there's a A transpose into A. If A has condition number kappa, A transpose A has condition number kappa squared. Okay. These equations are also called the normal equations. Don't ask me why they're called normal. I don't know what is normal about them, but they're called normal equations in the literature.